Yes, complex numbers are matrices, and in this video I'll show you why everything becomes intuitive right away if you look at complex numbers as being matrices. So let's start with this video. Now, I, the imaginary unit, is represented by this matrix, and we'll see why and what does this mean in a couple of minutes. But firstly, complex numbers are represented in a grid. This is the complex plane. We have the real axis pointing this direction and the imaginary axis pointing this direction. Now, on the real axis, on the x-axis, this is the x-axis and this is the y-axis. On the x-axis, we have all the real numbers, so 1, 2, 3, 4, all the numbers like e, pi, fractions, etc. And on the imaginary axis, we have all these numbers multiplied by I, the imaginary unit, this weird identity. Now, what's important about this plane? Now, for the time being, let's ignore the y on the imaginary axis. Let's think of this grid as being a Cartesian grid, so a plane, and you can identify a point in the plane using two coordinates. So, for example, this point P has two coordinates. One coordinate, that is the x-coordinate. We first specify the x-coordinate and then the y-coordinate in brackets with a comma in the middle, and in this case the x-coordinate is 1, 2, 3, so 3 spatial units, and on the y-axis we have just one unit. So this is the point 3, 1, and we can also specify this point as a vertical grid instead of as a vertical collection of points, vector. We call this vector. So 3, the x-coordinate first, and then the y-coordinate underneath the x-coordinate. So 3, 1. This is the point 3, 1. And we can also look at this point as being the tip of a vector starting from the origin. And this is what vectors are. We specify a grid, a Cartesian plane where the origin is. We specify a scale for each axis. So basically what we mean by 1 on each axis. Basically we define the length of the unit on the axis. And this is a vector specified in space, a point, an arrow, whatever, represented by two components in two dimensions. Now, this vector can be represented as a sum of two smaller vectors. These two purple vectors, these are univectors because they have a length of 1. This is x hat and this is y hat. Now, the coordinates of x hat are 1 along x and 0 along y, and for y it's 0 along x and 1 along I. If we sum these two vectors and we scale them by multiplying them by a number, meaning they can get longer and shorter, we can recover this point P as a sum of we call it a linear combination of these two vectors. Now, what happens if we take a number? Let's take a number, for example, 4 or 3, perhaps. Yes, let's use 3. And what happens if we multiply 3 times I? Well, we get the number 3i. But what if we look at numbers as vectors in this notation, in this vector notation? Let's see what happens, because it's very interesting. Now, the numbers along the x-axis have 0 as the y component and have a number along the x component, and those are and this is I would say the vector representation of real numbers. Instead, along the y-axis we have a 0 as an x component and a number as a y component. So bear in mind, we can represent real numbers in this way and imaginary numbers, meaning real number times I, in this way, simply because they lie on this grid. Now, If we take the number 3 that we specify using this convention as, so let's say 3 equals 2, even though this equal means it's represented by the number 3, 0, the vector 3, 0. The number 3i, so this is 3, the number 3i is this number here. It lies on this imaginary number line. So we need to specify the components. 3i is, the x component is 0, the y component is 3. So multiplication by I, if we take the number 3, this is the number 3, and we multiply this number times I, so let me write I here, we get 0, 3, and this is the number, the vector representing 3i. So I is an object that turns 3, 0 into 0, 3. And you see, this is not a sort of rescaling, because if we multiply a vector by a number, we just get the vector scaled by some component. Instead, here we're doing something more complicated, because the coordinates are very different, and the angle between the vector is different, because this is the number 3, the vector representing the number 3, and this is the vector representing the number 3i. So you see there is a rotation of 90 degrees. And this is very important, because we will represent I as being a linear transformation. Now, linear transformation meaning we take a vector and we move it around in space, we rotate, we may rotate the vector, and I really rotates vectors. And the object that does that is a matrix. A matrix is a set of instructions to tell the vector how to move in space. So we have our vector 3, 0, and we have to obtain the vector 0, 3, and we need something that does that. This is I, and it is a matrix, a set of instructions. Now, if we have this matrix, the first column tells us the coordinates of the x and y coordinates, so x here and y underneath the x coordinate of the x vector, unit vector, and here instead the x and y coordinates of the y vector, and these coordinates are of the x vector after the transformation and the y vector after the transformation. So if we multiply them by I, we saw that we rotate in 90 degrees. So the x hat vector and the y hat vector also rotate by 90 degrees. So this is what happens after the rotation. The x vector gets rotated by 90 degrees. And now the y vector that was previously lying along the imaginary axis is now lying on the opposite direction of the real axis. This is a rotation of 90 degrees. And now we have to specify the arrival components of these two vectors. So the x vector now has 0 x coordinate, 1 y coordinate. So let's specify them here. 0 x coordinate, 1 y coordinate, and the y unit vector as -1 along x and 0 along y. See, this is a matrix representing a 90 degrees rotation counterclockwise. And this is I, because multiplying that by I does the same thing this matrix does. So this is why we represent I with this matrix. See, it is the same matrix. Now, if we were to kind of apply a transformation that does nothing, we leave the vector unchanged. So if we have 3, 0 and we want to get 3, 0, we multiply by 1. So we can represent 1 using a matrix, and the matrix is Well, this is the x vector that remains unchanged. So 1 along x, 0 along y vector, 0 along x, 1 along y. And in fact, this is the identity matrix. Identity matrix because if we multiply 1 by some number, we get the same number. Same thing, we multiply this matrix by a vector, we get the same vector. Now, an interesting thing happens because something very confusing normally arises when we say, okay, I squared equals -1, and we say, what? Why should I squared be equal to -1? Well, because it is the square root of -1, and that is very confusing. By using matrices, this is very, very simple, because multiplying by I 2 times means rotating by 90 degrees 2 times. We first take this vector and rotate it by 90 degrees, and then we rotate it by another 90 degrees. So we get an overall rotation of 180 degrees. So I squared equals to 0 minus 1, 1, 0 applied twice, and it's a rotation of 180 degrees. And let's try to find out what this matrix is. Now, 190 degrees rotation, and the x unit vector lands here. So this is x hat, and this is the y unit vector, y hat. Now let's find the coordinates. X hat has coordinates -1, 0. So -1, 0. While y has coordinates, y hat has coordinates -1 along y, -1, 0, x and y coordinates of the x vector, x hat vector, and y has coordinates -1 along y, so -1 here, and 0 along x. And see, this is basically minus the identity matrix. So this is the same as writing, let me use another color, for example blue. This is the same as writing minus, because we can factor out -1, but I won't bother writing 1. So -1, 0, 0, 1. This is the identity matrix. So multiplying a number by I squared is the same as multiplying that number by -1. And in fact, I squared equals to -1. See, this is a lot more intuitive than before. Now we know why I squared equals to -1, because what it does is minus what the identity matrix does, 180 degrees rotations. And that's it for this video. In the next videos, we'll further investigate this weird behavior of y as being a matrix. Thank you so much for watching my videos, and let me know in the comments what you like to see in another episode, and we'll see other things about complex numbers in the future. And don't forget to subscribe to my channel and share this video with your friends. See you next time. Bye.